Okay, so 6:03. Hello, everyone. My name's Walker Battalozo. I'm the president of EERI. I want to welcome you to this talk. We're hosting Dr. Diane Moug from Portland State University. She's going to be giving a great topic on the field trials of microbially induced desaturation for earthquake liquefaction mitigation, and I think it should be great. We're recording this. I'm going to be uploading it to our YouTube in case you want to go back and watch this amazing presentation again. Or if there's someone that wanted to make it but wasn't able to, you can let them know and we'll put that on our website later. So without further ado, here she is. Thank you so much.
Okay, well, yeah, thank you very much for having me at this and allowing me to present here. Yeah, it's kind of funny to be presenting for OSU when it would be such a short trip, but it is what it is. Like Walker introduced, I'll be presenting field trials of microbially induced desaturation for earthquake liquefaction mitigation. This was a project that we undertook summer 2019. So a lot of the results and the processing of this project are still ongoing, but I'll be presenting some of the results up to this point and some of our kind of thoughts for going forward in the future. And feel free to stop me along the way, either with questions in the chat or just interrupt me if there's anything that I can clarify for you all. So a bit to start on the motivation of this work and thinking about the liquefaction hazard specifically in Portland. What we're concerned about in Portland is the liquefaction hazard or the seismic hazard due to the Cascadia subduction zone, possibly producing a magnitude 9 earthquake. And that subduction zone fault is located about 100 kilometers off of the Pacific coast. We're also concerned about shallow crustal faults that are much closer and within Portland. Smaller magnitude earthquakes are produced from these faults, but because they are so close or proximal to Portland, we can still expect strong shaking. And so this figure that I'm presenting here at the bottom, this is sort of encompassing some of the liquefaction hazard that we have in Portland. So strong shaking in Portland, potentially leading to liquefaction of these soils in Portland. And you see that particularly along in the dark red, along the Columbia rivers and the Willamette River is where Dogami, they consider these to be soils with high liquefaction susceptibility. And these align with what are typically loose, young, liquefiable silt soils along these rivers. There's particular concern about the liquefaction hazard in the Critical Energy Infrastructure Hub, or the CEI Hub. And this is an area along the Willamette River, shown here. And this, there's many fuel storage tanks along this river, or within the CEI Hub. And the hub itself is where about 90% of Oregon's fuel is handled, including all the fuel for the Portland International Airport. And so there's concern that the strong earthquake shaking can cause liquefaction of these silty soils, and that deformation that can lead to deformation of the ground or settlement of the ground that then will put strains and cause damage to these fuel storage tanks. And I've kind of clipped some images here of the fuel storage tanks that are located along the Willamette River. So there's concern that this can cause an environmental impact if the fuel spills into the Willamette River and migrates down to the Columbia River. Can cause health impacts if there's hazardous materials that vaporize into the air or potentially burn. And then economic consequences as well, that this is Oregon's fuel supply. And if there isn't access to it following an earthquake, that will really hinder recovery from the earthquake itself. So when we think about these silty soils and how we can mitigate the liquefaction hazard, particularly when we think about the soils beneath the fuel tanks, the primary method for mitigating these silty soils is deep soil cement mixing. And these are some images that I got from Condon Johnson Associates. So on the left here is a schematic of deep soil cement mixing, where the cement is mixed with the soil in a grid pattern, and that helps to reinforce the strength of the soil as a whole. And it kind of acts like rebar does in concrete, and as in it provides strength for the whole element. And then there's a video here again from Condon and Johnson showing this deep soil cement mixing occurring from one of their projects. But what you can kind of take away from this is that this is quite an invasive method. This isn't something that can be reasonably applied beneath an existing structure, such as those fuel storage tanks. And where we are right now in geotechnical engineering practice is that we don't have any economical options for mitigating liquefiable silt soils beneath existing structures. So that's sort of where we're starting to look of, okay, what potential solutions are there for mitigating silt soils beneath existing structures, such as those in the CEI hub. And so that's where potentially using desaturation for mitigating liquefaction comes in. This slide is presenting the results of a study by Hay et al. In 2013. And what this showed was that a small amount of gas in the soil's pore fluid can mitigate liquefaction by reducing pore water pressure buildup. So when loose saturated soils are shaken in an earthquake, the soils want to contract or compress, but we have water within that pore space. And so the soils cannot contract, and instead they build up excess pore water pressure and lose the strength. So if we can reduce that buildup of excess pore water pressure, we can mitigate the liquefaction hazard. So these shake table tests, these were performed with loose sands in a shear box on a shake table. And then on the left here is showing the results of 3 pore water pressure transducers that were embedded within that shear box, within the saturated soil. So with this completely saturated soil, showing the results of time, where shaking starts at about 2.5 seconds, and then the water head, or the water pressure that builds up due to that shaking, you can see that there's an increase in excess pore water pressure during shaking, and then that dissipates after shaking stops. If these tests, the saturation was then reduced to 95% saturation, so introducing some air into the soil's pore fluid, and you see that the excess pore water pressure buildup is much less than that fully saturated soil for the time of shaking. And we see an even further reduction when the saturation is reduced to 80%. So introducing some air into the pore fluid, or gas into the pore fluid, reducing saturation of the soil, limits pore water pressure buildup. There's also results by O'Donnell et al. In 2017, and these looked at liquefaction resistance, or cyclic strength of the soil as saturation decreases. So on this plot shown here, this was performed with lab testing in a cyclic direct simple shear device. So a small soil element that's subjected to cyclic shearing. Plotted here is the cyclic shear ratio, or the strength of cyclic loading applied to the soil element, and then the number of cycles that it takes to trigger liquefaction or to fail the soil cyclically in that loading. The dark dashed line on the bottom here is a fully saturated specimen. And what we see here is that, let's say, for example, at a cyclic shear ratio of 0.3, it takes about 5 cycles to trigger liquefaction. And then at lower cyclic shear ratios, it takes many more cycles to trigger liquefaction. That soil, if the saturation of that soil element is then reduced to 99%, the authors reported a notable gain in cyclic resistance of the soil. So now it takes, let's say, for 5 cycles of cyclic loading, that's a cyclic shear ratio of 0.4. And then if the saturation is reduced further to 97%, we see an even further gain in liquefaction resistance. So what this tells us is that by reducing saturation, we can reduce pore water pressure buildup in the soil, like shown on the last slide, and we can also increase the liquefaction resistance of soil as well. And so what we started to think about, or what we used for this project, is a way to induce desaturation in soil using microbes that exist or that are native to the soil. And this is microbially induced desaturation, and I'll be referring to it as MID probably throughout the rest of the presentation. And the idea behind this treatment method is that we can introduce a treatment solution into the subsurface soils that can migrate beneath an existing structure. And this treatment solution will stimulate native bacteria or microbes that are already within the ground to perform a denitrifying reaction. And that denitrifying reaction, it produces as some of its products nitrogen and carbon dioxide gas. This gas then displaces some of the water in the pore space and desaturates the soil. And this can potentially lead to mitigation of the liquefaction hazard of the soil. This image here is showing from Sean O'Donnell's work, showing some evidence of microbially induced desaturation. Shown here, this is a sand grain. These are two sand grains, one here and one here. And the reaction that they were looking at included also precipitation of calcite. And so these crystals here, this mineral, is calcite precipitation from the microbial reaction. But that precipitation, it developed around a gas bubble between the two sand particles. So this image is showing evidence of microbially induced desaturation, and that evidence comes from having the precipitation of the calcite between the sand particles as well. And I'm getting a question here. So the question is the gas type used dissolvable in the surrounding water under the saturation phase? And that is a great question. I'm sure that this is kind of beyond my background when we start talking about kind of the chemical side of this. Potentially, I'm sure under certain conditions it could be dissolvable. One thing that we are looking at with this project is kind of the long-term how these gases sustain in situ long-term. As far as I know, the solubility of the gas isn't a big factor. What we are more concerned about actually with this gas in situ is migration of the gas. Is it not in full screen? I am so sorry, I apologize. It is on my other screen. Let me share this. Okay. How's that?
Perfect.
Okay, I'm sorry about that, everyone. So you probably weren't even seeing my pointer either. So, okay, this is my pointer now. So what we're concerned about, or initially concerned about, was gas migrating out of the pore space and then leading to resaturation of the soil. And so one thought was that by applying this treatment method to silty soils, the small pore space in silts compared to sands or coarser grained soils could potentially limit migration of gas out of the soil and lead to longer lasting saturation. So in order to look at MID for liquefaction mitigation, we did 2 field trials of this in Portland in the summer of 2019. And the objectives of doing these field trials were to look at the way that MID performs when it's applied at the field scale, to look at how it performs when it's applied in silty soils, and then to start to examine its effectiveness for liquefaction mitigation. And these 2 field trials were, as far as we know, the first full-scale field trials of MID for liquefaction mitigation in the US. So with that motivation of the project behind us, going forward in this presentation, I'll first talk about the subsurface conditions at the 2 field trial sites that we worked at, one called Sunderland and one called Harborton. I'll present the MID treatment solution and its application, and then also discuss some of the monitoring data that we collected and the results from those data. And finally, I'll discuss some of the T-Rex large shaker truck testing that we did at the site to perform in situ cyclic testing, and that was done at the Sunderland site. So starting with the subsurface conditions at Sunderland and Harborton sites. This is that map that we showed on the first slide showing the liquefaction hazard in Portland. The two sites that we selected for this project are within Dogami's estimate of highly liquefiable soils. One site was the Sunderland site near the Portland airport, and the second site is the Harborton site within the CEI hub. The Sunderland site, an image here of the project in full swing, and with the plane in the background to assure you that it is close to the airport. So the Sunderland site is located along the Columbia River, and the soils at the site tend to be floodplain deposits from the Columbia River. These were silt soils with an average plasticity index of about 14, and with the Brian-Sanchio criteria, we considered them to be moderately susceptible to liquefaction. On the lower left-hand side here is showing just a generalized stratigraphy of the site. It was fairly uniform, and these images on the right of some split spoon samples as well kind of show that uniformity of the soil, where we have just a generally uniform low plasticity silt. The water table at the site was about 1 meter below the ground surface, and then we've also seen some seasonal fluctuations in that water table as well. When we performed the trial during the summer, the water table is probably at its lowest extent, or one of the lowest extents. So when we looked at treating the soils at the Sunderland site with MID, we chose an interval to treat the soils from about 1.5 to 6 meters below the ground surface. The Harborton site, our second site in the CEI hub, this is showing an image of the site here as well when the project was in full operation. And this site itself is mostly composed of alluvial deposits from the Willamette River, and as well as some soils that were dredged from the river and placed at the site as well as fill. What we saw at the site was something slightly less uniform than at the Sunderland site, and we saw a fair amount of interbedding of the soils at the site, where we had non-plastic silt or fine sand layers interbedded with low plasticity silts. And again, we have a similar liquefaction susceptibility according to the Brian-Sanchio criteria. So these split spoon samples on the left I thought were pretty interesting, particularly this one at the top showing a very soft fine sand that we pulled up with the sampler. And we saw this in a couple instances when we could recover a sample of it, just showing how showing a fairly saturated and loose sand where this would be concerning, particularly for liquefaction. So at this site, we targeted for MID treatment, low plasticity silts that were interbedded with non-plastic sandy silts. And this was deeper into the ground at about 3 to 4.5 meters below the ground surface. So a smaller treatment interval than at the Sunderland site. So going to the way that the treatment solution was applied at the site and the treatment solution itself. The treatment solution, it was composed of calcium nitrate and calcium acetate, where these chemicals were placed into these mixing totes, and then water was added to them, and a trash pump was used to circulate them in order to dissolve them into solution. At the Sunderland site, when the treatment started, we also added some trace elements of Miracle-Gro and Epsom salts, and that helped to stimulate the reaction. But after about a week of the treatment, we found that the reaction was occurring rapidly enough on its own that we no longer added them at the site. And these are two of our graduate students that worked on this project that were working on mixing the chemicals at that day. So the treatment solution reaction, and I'm not going into depth for this here. There's more information on the treatment solution reaction in Stallings Young et al. 2020 paper. But I'm just kind of hitting on the main points here. The denitrifying reaction of the microbes is both a catabolic and an anabolic reaction. With the catabolic reaction, that's where the acetate and the nitrate in solution from the calcium acetate and calcium nitrate those react to produce nitrogen gas and bicarbonate, among some other products. That catabolic reaction, it also generates a little bit of energy, and then that helps to stimulate the anabolic reaction. And it's pretty similar, at least from my understanding of these chemical reactions, but it does produce some biomass as well as nitrogen gas and bicarbonate. And this biomass, it was something that was more of a challenge to this project, since it tended to build up in the plumbing and the well screens as well. So the nitrogen gas was our primary product that we were after to generate in the subsurface and desaturate the soil. But in addition to the nitrogen gas and calcium and biomass, the reaction may have also produced, with some further reaction, calcium carbonate precipitate and CO2 gas. But again, like I said, those biogases, nitrogen gas and carbon dioxide, those are the primary products that we were after, because we want to desaturate the soil. And the idea is that these two products would help to change, we could leverage and take advantage of to change the engineering properties of the soil or the behavior of the soil. This image here is just showing an example of that biogas in these fine-grained soils. So these are examples of soil and water that were taken from the Sunderland site. And then they were just mixed in the lab in a slurry with the specimen on the left with calcium acetate and calcium nitrate, our treatment solution, and then left to sit in the lab and see how the MID reaction took place. The specimen on the right is a control specimen. So same soil, same water from the Sunderland site, but without those treatment chemicals added to it. And what we see is that the MID treatment, it does stimulate the microbes, and we see this in the lab. Then they're producing biogas, and we get these pockets of biogas that's showing up within our soil in the lab. So this is under lab conditions, meaning that it's more or less atmospheric pressure that this is subjected to. Whereas in the field conditions in situ, we expect the soil to be under more pressure and total stress, which would cause that gas to compress, and maybe those pockets won't be as large as shown here. So in order to apply the treatment solution to the subsurface, we used a combination, we used an injection well shown here to introduce the solution into the subsurface, and then 4 extraction wells that were installed spaced equally from that injection well. They were installed 3.5 meters from the injection well. So the treatment solution, once it was mixed and then diluted, was fed into the injection well, both through a gravity feed and then also an inline pump that added some extra pressure head in order to kind of overcome both low permeability at the site and also any biomass that may build up within the well screen or the filter pack. These images here, they show, again, those 2 graduate students, Kayla and Melissa, mixing the calcium acetate and calcium nitrate in the mixing tote. That then gets transferred into this injection tank and diluted to the required solution concentration. From the injection tank, the solution is then fed to the injection well, where we have the injection well head shown here. Just out of the screen here would be the inline injection pump. And then we also have a pressure gauge at the top so that we can see what injection pressure we're applying to the treatment solution, and also ease off a little bit if we feel like that injection pressure is getting too high. The extraction wells, they had 2 purposes. The first was to give us water from the site, native groundwater, so we could use that for the treatment solution and to mix it. Second was that we were hoping that they could provide some drawdown that would encourage the migration of the treatment solution from the injection well to the extraction well. So we wanted some drawdown, but we didn't want so much drawdown that we were drawing down into our targeted treatment interval and inducing desaturation that way. So in order to limit the drawdown in the extraction wells, and then also not allow the extraction wells to run dry, we set up a control system where that limited or that only drew down the water in the extraction wells to a given level or a set level. And so these are the submersible pumps that were lowered into the extraction wells. They extracted water that then went into the extraction tank for storage and also for some monitoring. And then within these submersible pumps, we also included a float switch that when the water level dropped below a certain depth or dropped below the float switch would drop down as well. And it would break the circuit from the battery to the submersible pump. Then the water level, once it was allowed to recover, would bring that float switch back up. And this circuit board here is showing some timers and motor controls as well. So those timers would say, okay, the water level's back up. It would wait about 60 seconds and then allow the pumps to turn back on or allow the single pump to turn back on. And we also have a motor control here that just allowed us to play with the flow rate from those pumps as well. So that they maybe weren't cycling quite as much as if it was pumping at the full capacity of the pump. This is a figure of the Sunderland test area when it's fully set up. We have the central injection well with the inline pump shown here, and then the 4 surrounding extraction wells. Between the injection well and this extraction well, we also installed a vertical sensor array of Tero sensors. And I'll discuss those a little bit later, but that's the location it is there in between those 2 wells in the middle of the targeted treatment zone. We also shown here is another sensor array that we used for both T-Rex testing and to perform crosshole seismic wave velocity measurements regularly throughout the treatment and after the treatment. At the Sunderland site, I showed that treatment interval on the earlier slide. And again, so the wells are screened from 1.5 to 6.1 meters depth. We consider that to be approximately the targeted treatment interval. And so with the radius from the injection well to the extraction wells, and then that screened interval, that's an approximate treatment volume of about 16 meters cubed. We have a very similar setup at the Harborton site with the injection well in the middle of the 4 extraction wells. There's also the Teros vertical sensor array in between the injection well and extraction well. And then this slide is also just showing a mixing tote where we have calcium acetate in solution in an extraction tank on the left there. Both the injection and extraction wells at this site were screened from 3 to 4.6 meters depth. And so our targeted treatment volume was about 5.5 meters cubed. So about a third the size, about a third smaller than at the Sunderland site. So we applied the treatment solution for about 4 weeks in that we injected it through the injection well and ran the extraction pumps for about 4 weeks. And during this time at the 2 sites, we introduced about 60% of the pore volume in that targeted treatment zone into the subsurface. These figures here are showing the treatment injection volume over time from our start of treatment. The Sunderland site on the left, and you can see that the treatment injection volumes, they started maybe a little bit slow as we kind of nailed down our methods and did some troubleshooting. But then after about 15 days of treatment, we understood the proper injection pressures and how to overcome the biomass that builds up within the injection well and within the plumbing lines as well. And you can see that our rate of treatment injection increased quite a bit and stayed steady from about 15 days. The Harborton site, we started treatment at that site about a week after treatment started at Sunderland. And so we were able to keep about a steady injection rate at the Harborton site as well. And with both these sites, like I said, the volume of solution that was introduced into the subsurface relative to the size of the targeted treatment zone was pretty similar between the 2 sites. And we think that it was about 60% of the pore fluid volume within the targeted treatment zone. So let's discuss some of the data that we collected from this project, both during the MID treatment and then and then some of the results that we've gotten after the treatment as well. So our objectives of doing monitoring at these sites was primarily to look at changes in saturation ratio. We wanted to see if this microbially induced desaturation was indeed desaturating the soils at these sites. We also wanted to look at migration of the treatment solution. Was the treatment solution migrating uniformly throughout that targeted treatment zone, or from the injection well to the extraction wells? Or was it finding concentrations in preferential pathways? And then we also wanted to look at the progress of the MID reaction and observe whether those chemical reactions were occurring in situ. The monitoring for these projects included CTT divers, shown here, and these are submersible sensors that we placed in the injection and the extraction tanks. It included TERO sensors, which included that vertical sensor array between the injection and extraction well. And these sensors, it has 3 pins, and those insert into the sidewall of a borehole, and then we backfill it with soil. There's also the T-Rex sensor array, which was only present at Sunderland. And this was used to measure seismic wave velocities through crosshole measurements. We also, at both sites, actually did seismic cone penetration measurements. And then at the Sunderland site, only there was direct push crosshole seismic measurements. The T-Rex sensor array was also used to measure cyclic induced pore water pressure for testing that was done with the T-Rex shaker truck before MID treatment and then after MID treatment. And that's this picture shown here, the schematic of the T-Rex shaker truck. Again, the TERO's vertical sensor was located between the injection well and extraction well. And then at the Sunderland site, we have the T-Rex sensor also located within the targeted treatment zone between the injection well and an extraction well. So the CTT divers, these were primarily used to look at the electrical conductivities in the injection and the extraction tanks. And electrical conductivity was useful because it's related to the salinity of the solution. That calcium acetate and the calcium nitrate that we dissolved in the for the treatment solution, those are primarily salts. But then as the reaction takes place, the products are primarily gases, biomass, and maybe a little bit of precipitate. So that's removing the salts from solution, which therefore we should see a decrease in the electrical conductivity as the MID reaction progresses. So a sensor for electrical conductivity may initially see a rise in electrical conductivity as the treatment solution reaches that location, but then a decrease as the MID reaction takes place. So these images here, they're showing the electrical conductivity in the injection tank, which is the blue line for both the Sunderland and the Harborton sites. And we expect this electrical conductivity to be high because this is right after the treatment solution has been prepared. We expect it to stay high and then for the treatment solution to be injected in the ground, ideally before the MID reaction takes place. The red is the electrical conductivity in the extraction tank. And again, we expect this to increase a little bit as the treatment solution migrates to the extraction wells, but then potentially decrease as the reaction takes place. So starting with the Harborton site down here on the bottom, we see sort of what we expected. The blue is the injection tank again, and then the extraction tank, initially the electrical conductivity is as low at about background levels of about 1 or 2 millisiemens per centimeter. And then the treatment solution reaches 1 or more of the extraction wells, and the electrical conductivity stays at about 5 millisiemens per second. So it's lower than that in the injection tank, and this may be due to dilution with other groundwater that's not the treatment solution, or it may be due to the MID reaction taking place a little bit before it reaches those extraction wells. And then after about 10 days of treatment, we see a decrease in the electrical conductivity of the extraction well. And this may indicate that at that point, the MID reaction is occurring quickly enough or at a high enough rate that most of the reaction is taking place before the fluid reaches the extraction wells. So that at this point, this may be an indication that the MID reaction is occurring in situ within that targeted treatment zone. The results at Sunderland were a little bit different, kind of showing that there's two different characteristics to these sites. And I just want to focus in on what's happening between about August 28th and September 2nd. What we're seeing at the Sunderland site is that at the extraction well, we see these spikes in electrical conductivity. And those increases, those are related to when injection in the injection well of the treatment solution, when it starts. So there's some indication that there is a fairly direct hydraulic path between the injection well and at least one of the extraction wells, where we see this sudden increase in electrical conductivity. And when I say sudden, it was actually about a 30-minute delay between the start of injection and when this electrical conductivity picked up in the extracted water. So this indicates that at Sunderland, there's maybe this preferential pathway between the injection well and one or more of the extraction wells that we don't see the same thing at the Harborton site. But either way, we see that the treatment solution is migrating throughout that targeted treatment zone towards the extraction wells. Electrical conductivity was also measured with these TERO sensors. And so this is where we could look at the treatment solution vertically, since the sensors were installed in a vertical array midway within the treatment zone. So starting with the Sunderland site, I won't spend too much time on this site. The sensors, they weren't installed correctly at the Sunderland site. They were, we had some trouble with this being our first install of these sensors, and the sensors ended up just being placed in the hole and then backfilled with soil and then placed, backfilled, placed, backfilled. But we still do see some notable information from the Sunderland site sensors, notably that we do see increases in electrical conductivity at various depths in these sensors. And interestingly, we don't always see these at the same date. And we also see these increases above the screened interval of the wells, where this sensor at 0.9 meters, which shows an increase at about 21 days, that was above the targeted treatment zone. So there's some indication here that we got some migration of the treatment solution outside of that screened interval. The Harborton site, these sensors, they were installed as intended and inserted into the side of that borehole and then backfilled. And this gives us a trend, much more what we expected to see, but we still get some interesting information from it. So we see that the treatment solution potentially arrives at the deepest sensor at 4.6 meters about 6 days after the treatment starts. And this sensor is within the targeted treatment interval. We see that increase in electrical conductivity followed by a decrease, indicating that the MID reaction is occurring. About 9 days into the treatment, we see the treatment solution reach 4 meters, and then maybe 10 days, the 3.4 meter sensor. And then after some delay, we see the electrical conductivity increase at the 2.1 meter sensor. And this sensor is also outside of that treatment interval. So interestingly as well, we maybe had some migration of the treatment solution vertically outside of the treatment interval at the Harborton site as well. What's also interesting about the Harborton site is that there does seem to be a preferential pathway where the treatment solution reached that 4.6 meter sensor first, but the solution did also reach the other sensors after a few more days. So even though there were preferential pathways, we still have migration of the treatment solution to other parts of the treatment zone. The TERO sensors, they also measure dielectric or electric capacitance of the soil. And this electrical capacitance, it can relate to the volumetric moisture content or the moisture content of the soil. And so this was useful to see and look at relative changes in moisture content throughout treatment. We still need to look at these values and validate them with measurements of moisture content at the site, but they are useful to see those relative changes in moisture content. So as the soil desaturates, we expect the ratio of water to soil to decrease. We expect the moisture content to decrease. And that's what these measurements show as well, is that there is a decrease in the moisture content where these sensors are installed, both at the Sunderland site and also at the Harborton site. And these moisture contents, we could then relate to the saturation in situ and say that changes in moisture content also relate to changes in saturation. We did assume initial values of saturation at either 100% or 98.5%, and these were based on some other measurements that we made. And so what we see with these approximated saturation ratios is that at the Sunderland site, we got a drop in saturation ratio to potentially between 80% and 96%, but more importantly, we saw a decrease in saturation. This is also, that decrease in saturation is also supported by measurements of saturation on Shelby tube samples. This is the result here of a sample that was sampled before treatment, and then a sample that was obtained post-treatment. Again, we're not, these saturation ratios, they may be a little bit off and maybe a little bit underestimated, where we would have expected this one to be nearly 100% saturated, and this post-treatment sample to be probably at a higher saturation ratio. But they do show a decrease in saturation, despite the difficulties of testing and measuring saturation ratio. We see something similar at the Harborton site, where we get a decrease to about 90 to 95% saturation according to these TERO sensors. And again, support that the site was desaturated from a Shelby tube sample that was measured. So we found that directly measuring the saturation ratio from the Shelby tubes, it was challenging, not only because there's potentially moisture loss as you're sampling the soil and then preparing it for transportation, transporting it and storing it, but then also that when the soil is taken from the subsurface, there's possibly the gas within the pore space, when it's brought up to atmospheric pressures, that gas will expand in volume. So these saturation samples, they do have a correction for the ideal gas law applied to them, but we still see that the saturation is underestimated. So another way to look at changes in saturation at these sites was through a pressure wave velocity measurement. When a pressure wave is imparted on saturated soil, the pressure wave will travel through the water in the pore space. And so when you measure the velocity of that P wave, you're measuring the P wave velocity of water. But what we also find is that when saturation drops to about 98.5% or drops just a little bit from 100%, we see a fairly precipitous drop in the P wave velocity, in the measured P wave velocity. This is shown here from the O'Donnell 2016 dissertation data from some P wave measurements at various saturation ratios that were performed on Ottawa sand. What you see is that at 100% saturation, we have a high P wave velocity, on this plot about 2,000 meters per second. And then as saturation decreases, we have a drop in P wave velocity to about 400 to 800 meters per second, depending on the confining stress on the soil. So if we measure at the site initially high P wave velocities that then decrease, that's an indication that there is desaturation introduced in the subsurface soils. In order to measure the P wave velocity, primarily we were looking at measurements through a Crosshole seismic array. And this is this is part of the sensor array that was installed at the Sunderland site. So the Crosshole array, a schematic of it is shown here. And there are 4 seismic source rods that are installed at different depths in the subsurface. And those seismic source rods allow us to apply a seismic wave from the rod that then travels through the subsurface, and its arrival is detected by the first geophone and then the second geophone. So we can look at the the time it takes for the wave to travel from geophone 1 to 2 and relate that to a velocity. So there are 4 depths that we installed these crosshole measurements at. Up here in the upper right, these are the seismic source rods at the ground surface. And then at the left here is one of our graduate students, Kayla, with her instrumented hammer, also shown here, performing these crosshole tests at our site. And the advantage of this is that they were fairly low effort. So once the sensor was installed, we could perform these tests quite frequently, both before MID treatment, while the treatment solution was being applied. And then also we can look at the seismic wave velocities after the MID treatment. These are some examples of the P wave velocities measured before MID treatment. So we get kind of our baseline values. On the left here are the P wave velocities at the Sunderland site. And this is showing 2 different sources of P wave measurement. The symbols are for direct push crosshole measurements which were performed by the researchers from UTexas. And in this, the source and the geophones are advanced down through the subsurface. So we can measure a lot of depths and get a nice P wave velocity profile from these measurements. What we see here is that we have high P wave velocities around 1600 meters per second, which we'd expect for saturated soils, that decrease quite rapidly at about 2.25 meters below the ground surface. So from this, we could interpret that our soils at the Sunderland site, when these measurements were performed, were about fully saturated, or at least greater than 99.5% below 2.25 meters below the ground surface. The solid line here, this is from seismic cone penetration measurements. So it's the seismic cone is advanced through the ground and the source remains at the ground surface with the geophone on the cone that can detect that wave's arrival. We see here that the measurements may not have been, they didn't capture the fully saturated P wave velocity values. They tended to be a little bit underestimated, but we still do see, at least with the advantage of having the direct push crosshole data as well, we see a similar drop in P wave velocity at about 2.25 meters below the ground surface with the SCPT measurements as well. And this was useful for at the Harborton site when we only had seismic cone penetration test measurements. We could, knowing what we know with the direct push crosshole measurements, we could say that this decrease in P wave velocity about here was likely due to a change in saturation at the Harborton site. So we estimate that the Harborton site is saturated from about 3 meters and deeper. So this figure is showing the P wave velocity measurements that were performed at the Sunderland site, both before the treatment started, during the treatment, and then after the treatment. So before the treatment, with the 2 depths at 2.55 and 4.45 meters below the ground surface, we see those initially high P wave velocity values, and they remain high until treatment starts. And then about 10 days into treatment, there's a drop in the P wave velocity measurements. And all of the crosshole measurements decrease and remain low at about 400 to 500 meters per second for all of those sensors. So this plot is showing the P wave velocities. It looks like about 130 days post-treatment. And so this indicates to us that, yes, the site was successfully desaturated according to these P wave velocity values, and that it's remained desaturated for about 4 months following treatment. We could look at some more sources of P wave velocity measurements. These are the baseline data that I presented 2 slides back, and then with the post-treatment data applied as well. So at the Sunderland site, shown here on the left, we have the direct push crosshole pre-treatment. We have the seismic cone data pre-treatment, and then the crosshole values that are showing that decrease to lower P wave velocities at the 4 depths. About 2 months after treatment finished, we went back with the seismic cone penetration test to measure P wave velocity profiles. And this allowed us to measure the profiles at various locations within the targeted treatment zone, which are these blue lines here. showing that at these 3 locations, we indicate that desaturation was present at those 3 locations. And then this line here, the dark dashed line, this was a location that was about 3.5 meters outside of or beyond an extraction well. And interestingly here, we also see a decrease in P wave velocity from those initial values, indicating that the treatment solution likely migrated beyond those extraction wells and induced desaturation outside of the targeted treatment zone. We see something similar on the right at the Harborton site. Again, the dark line are those initial values. And then the 3 profiles that were measured post-treatment, with the light blue being within the treatment zone, and then the dark line being outside of the treatment zone. We see evidence of desaturation or saturation below 99.5% for these 3 profiles, indicating desaturation both within the targeted treatment zone and potentially outside of the targeted treatment zone as well. The last part that I'll show here are just some Shelby tubes that we took, which we thought were interesting evidence of desaturation. So on the left here is a Shelby tube that was obtained pre-treatment. And on the right is a Shelby tube that was sampled about 2 months after we finished MID injection. These Shelby tubes were x-rayed at Oregon Health Sciences University. And this just gave us an idea where, or this just gives us an idea of how biogas has formed within the soil. So with pretreatment, we see a fairly uniform sample without evidence of desaturation. And then on the right, we see potentially these pockets of biogas that have developed in the soil and given it kind of that mottled appearance in these x-rays. So again, a difference between the pre-treatment and post-treatment, and a little bit more evidence of desaturating the soil. So the last part that I'll address today is the T-Rex testing that we performed at the Sunderland site, the in situ cyclic testing. And this was performed by NHERI at UTexas researchers. So the T-Rex testing was performed pre-treatment in July 2019. The treatment was applied throughout August and a week into September 2019. And then post-treatment testing was performed soon after the treatment finished in September. And the idea here was to compare the soil behavior and to measure changes in the pore pressure buildup between the pre-treatment and the post-treatment conditions. So these are pictures of the T-Rex shaker truck. On the left here is a schematic of the truck on top of the sensor array, where the base plate gets lowered down onto the ground surface, and then through that base plate, a sinusoidal cyclic motion is applied to the ground surface, and that motion attenuates with depth. So it's stronger at the ground surface and then weaker as it attenuates with depth. And this is a picture of the T-Rex shaker truck at our Sunderland site. This figure here is showing the sensor array. Again, this is the same sensor array that we used for those crosshole measurements. But now we have the T-Rex base plate located on top of the sensor array. And we have the geophones that create an element of soil. And from those geophones, we can estimate the amount of cyclic strain that's imparted on the soil, and then relate that cyclic strain to the pore pressures that develop within those soil elements with depth. So unfortunately, these pore pressure transducers, we didn't get a lot of strongly usable data from them, at least at this point. These two sensors at the top, those are, I believe that they're outside of the targeted treatment interval. And so we don't necessarily see the changes in desaturation from those two sensors. The 3P sensor turned out to be defective, and so we haven't gotten usable data from it. And then the 4P sensor at depth, right in the middle of our targeted treatment zone, was a little bit too deep, so we didn't get very strong measurements or very strong motions from the T-Rex, since most of the motion had attenuated by that depth. But we do get a little bit of data from the T-Rex testing as shown on this slide. So these two figures on the top are showing from a geophone that's placed within the ground both in the treatment zone and then well outside of the treatment zone, so we can compare the response. They're both showing for 2 shaking events, where the shaking event occurs by applying a motion that starts very small at small cyclic shear strains, measuring the pore water pressure buildup, and then progressing to stronger and stronger motions and building up those motions throughout a shaking event, and then starting over again with shaking event 2. So what these plots are showing is the cyclic shear strain that's imparted on the soil, and then the excess pore water pressure that's induced by these cyclic motions, where that is the ratio of excess pore water pressure normalized by the effective stress at depth. What we're producing in these plots is excess pore water pressure ratios of about 3%, where liquefaction typically triggers at about 90, 95%, 100% REU. So we're just applying very small motions to these soils to look at their responses. What we see with this plot here on the left, which is outside of the treatment zone, we see the pore water pressures increase as the cyclic shear strength, or the cyclic shear strain, or the motion, cyclic motion applied to the soil increases. And then on the right, this is within the targeted treatment zone, or within the treatment zone. And we got an unexpected result with these data, where we would have expected to see very little excess pore water pressure from the T-Rex shaking. And what we see here is just very little change in excess pore water pressure compared to the testing performed outside the treatment zone. So these points here, these are the points of excess pore water pressure right after shaking stops. What we did see was potentially a change in the excess pore water pressures that register after shaking stops, or for some period of time afterwards. And so plotted down here on the bottom is showing these differences. Where on the x-axis, we have time. The negative time is before shaking. At this point, between about 0 and 4 seconds, that's when the T-Rex shaking is taking place. And then what we see after is the excess pore water pressures that develop after shaking stops. The red line is within the treated zone, and we see an excess pore water pressure. We see it increase to about 6% post-treatment or post-shaking. And that's notably less compared to the excess pore water pressure ratio that developed in the untreated soils, which that rose up to about 10%. So we potentially see some change here if we look at excess pore water pressures that develop after shaking between the untreated and the treated zone. But the testing for this is ongoing, or the interpretation of these data are still ongoing. One thing to keep in mind, and one thing that we've been thinking about, is just the level of strains that are being imparted on these soils by the T-Rex. So this plot is showing a bunch of different data, cyclic data plotted together, but they're all plotting the cyclic shear strain, or the level of strain that's imparted on the soil, and the pore pressure ratio in response to that level of strain. Down here in the green, these are the T-Rex data from several of the sensors from T-Rex testing. And we see that compared to the other data, including these blue dots, which are resonant column torsional shear tests performed by UTexas researchers, which could get to a slightly higher cyclic shear strain and therefore produce a little bit more pore water pressure. And then these red squares and purple squares, which are cyclic direct simple shear tests performed by one of our graduate students at our lab, all the same soils for these colored symbols. We see at higher strain levels, we produce more excess pore water pressure still. So this gives us an indication that with the T-Rex testing, in order to see changes in the cyclic behavior of these soils, we may need to be testing at slightly larger shear strains and finding a way to impart larger shear strains on the soil to gauge the response to the cyclic loading and the impact that desaturation has. So those are our data from our field trials. So I'll just kind of go forward with the conclusions of this work and then discuss a little bit of where we see this going in the future. So we treated two sites in Portland that were underlain by liquefiable silt soils. We treated those with microbially induced desaturation. the targeted soils at both sites, we saw from the data that they were successfully desaturated. And that was indicated by decreases in P-wave velocity measurements. We saw it from sampling and testing of the, or measurement of the saturation ratio, and then also moisture content estimates from the TERO sensors. Electrical conductivity sensors in the treatment zone and then in the injection and extraction tanks also show that the treatment solution migrated throughout the treatment zone, and that we may have also seen a little bit of migration beyond the treatment zone as well, which was interesting. We saw that there were preferential paths, but despite those preferential seepage paths, the treatment solution still made it to most parts of the treatment zone, it appears. With the TRX testing, we potentially see some reduction of post-shaking pore water pressure values, but the lab testing and interpretation of those data are ongoing. So with that ongoing work, we're still testing these soils in the lab to get a better understanding of how desaturation or saturation ratio affects the cyclic behavior of these silty soils. We are planning to go out to, or we're continuing to go out to Sunderland site to continue to measure P-wave velocities with that Crosshole array and see if the P-wave velocities remain low post-treatment. And there's some plans also to do some sampling and measurements of the saturation ratio over time as well. And then finally, a little bit of chemical analysis of the soil samples, just to get a little bit more data on how the MID reaction was taking place in situ and how the treatment solution migrated in the subsurface. And that includes measurements of the calcium carbonate or possible bioprecipitate and ion chromatography analysis as well. So after that, just an acknowledgement of the research team that worked on this. It was a great collaborative effort, and as well as important partnerships that we had with the City of Portland and consultants and contractors as well. And with that, I'm sorry that went a little bit over time, but I'm happy to answer any questions. I don't imagine you all have classes to get to at this time. I can start with a question I have from Ali. How reliable is the data for pore pressure since the sensors are probably desaturated as well? That's a great question. So as we understand it, the sensors themselves were likely, or they were saturated, I believe, with mineral oil before they were placed into the ground. And so I believe that there's hope that the mineral oil itself remains, that the filter element or the piezo element on those sensors remains saturated with the mineral oil. But yeah, it's a good point, and potentially a way that, at least that we've discussed, why you see that almost like log linear trend between the RU and the cyclic shaking response for that first shaking event in the treatment zone. But actually, yeah, that sensor was lowered into the ground after the MID treatment had taken place. So it was likely saturated.
Hi, Diane. I'm not hearing any other questions. So I got, well, first of all, great. Thank you for the talk and spending this evening. Hold on, where's my video? Spending this evening sharing it with us. That's awesome. Thank you for that, for sure. I've had lots of discussions with Terry Jacques about trying to get P-wave data from cone trucks. I'm not sure who you used, but he seemed to have found some hurdle on the proprietary software of not getting that initial P-wave. Now, typically you don't see it very much when you hit the shear beam. So I'm curious, how did you provide the compression wave? Was it striking the rods or striking the shear beam? And then who was your cone pusher, and how can I start to get VP from cone data?
Yeah, so the cone was Cone Tech. They came out both before treatment and after treatment.
Gotcha.
Yeah, and so I was only there for the post-treatment cone testing, and it was, I believe, just applying a pressure wave to that beam from the surface.
Gotcha.
Instead of a shear wave. Yeah, Farnu Ming from Austin, he looked at the data. He seemed to think that it was okay. So
Gotcha.
yeah, and then I mean, as you saw with those data, like it's not perfect, at least compared to the UTexas results, but it still kind of gave us some indication of changes with depth.
Right on. Well, I have some ideas for well, they're not my ideas for interpreting VP, but we can get together offline and take a look at it. There might be something there, but awesome. Thank you so much for your talk. It's great. And I'm gonna have to run for dinner, but thanks again. Appreciate it.
Thanks, Armin. We'll see you. So I have a question from Amalish. How do you identify preferential path in the field, and how would you control for a best economic design in the future? That's a great question. So I think, are you referring to, like, if you had a site that you wanted to treat this with, how would you identify potential preferential paths? Okay, yes, all right. So I'm sure that there are many ways, and that hydrogeologists might kind of give you more thorough advice than I can, or engineering geologists. I think one way would be to know the geologic history of the site. Like, are there likely layered soils at the site? Is there maybe like some old sand or some sand layer that's going to be a preferential pathway? Are you likely to have stratified soils? So thinking about it that way might indicate that, yes, there's likely going to be a preferential pathway. And then, I mean, I could think of, you could potentially do slug tests. Maybe not this, because you have sedimentary soils, but you could do hydraulic tests that target different sections of the soil, so you can get kind of a hydraulic stratigraphy. One way would be the piezo cone dissipation test for a fairly rapid response, and interpret the hydraulic conductivity from those piezo cone dissipation tests and how rapidly dissipation occurs around the cone. And then, yeah, I'm sure that there are just others, like tracer tests even, that could be performed once the wells are already installed. How for best economic design in the future? So what's interesting is that what we found is that even that potentially there are these preferential pathways, but we still see the treatment migration occurring in the non-preferential pathways. And so that may be that the treatment solution, it may have been kind of like transferred quickly through those preferential pathways and then could migrate outside of them. Maybe that was only available to our site because they weren't necessarily continuous across the sites. But then there's, what was I gonna say? But then there's also potential that biomass, one of the products, could build up within those preferential pathways and then decrease the hydraulic conductivity of those as well. And so that what's at one point a preferential pathway may become a non-preferential pathway some ways into treatment. And so there's that to consider, and to something that we'll potentially look into as well. Are your CDSS tests constant volume, and how are you determining SR based on gravimetric relationships? Okay, first question, yes, our CDSS tests are constant volume. I believe that you have a similar setup at OSU for these cyclic direct simple shear tests. Yes, constant volume, and we were doing strain controlled tests for our specimens. How are you determining SR? So the SR for the samples, those are determined by doing wax tests. And Jiao, I'm pretty sure that you've done wax tests because I got the procedure from you and Matt for how to do it. And so yeah, the wax, you cover a soil specimen with wax, and then you measure the mass of it and the volume of it by submersing it in water in the wax, and then relating moisture content, and I believe you have to also assume a specific gravity to get the saturation ratio of the soil. And then I think that we also had some other estimates. Since we were trimming the specimens into the DSS mold, we could get a volume and then a density based on those as well. Okay, another question. Did you see a change in BP after T-Rex shaking? No, we didn't actually. And I can go back to that slide of the Crosshole BP tests. It's a great question. So let's see. On this plot, we have end of treatment injections at 27 days. And then I think that the T-Rex testing was probably done a week after this. So if we then go to about 34, yeah, we see that we don't see a notable change in VP, at least from before and after the T-Rex testing. Another question, you would have some swelling during sampling, so your calculated SR or saturation ratio may be different from in situ saturation ratio. Yes, absolutely. That's a really great observation. And that's one of the challenges that we had for like directly sampling and measuring saturation ratio. Just thinking back to the ideal gas law, PV equals nRT. The soils in the subsurface, those are subjected to in situ total stresses. And that's compressing the gas, the biogas that's been produced. Then we bring those soils up to the surface and now they're at atmospheric. And so, yeah, we do expect that the volume of gas in the soil samples did expand. The values for saturation ratio shown here, they do have a correction for the ideal gas law or with the ideal gas law to change the volume of the gas. We still are seeing these sort of funny saturation ratio values. So maybe it's a combination of insufficient use of the ideal gas law and potentially also just moisture loss during the sampling, storage, transportation, and then also testing as well. What is the minimum strain level you can apply with the DSS device? That is an ongoing discussion. We have some results that aren't terrible, I think at 0.1% shear strain. I tend not to put too much weight into those results. Just with with the displacement transducers and the load transducers that we have, I'm just not, I'm not convinced on how reliable they are. This is showing data at 0.1%, and we're showing that it is slightly above both the in situ and then the RCTS results as well. Like I said, I don't put a lot of value into these measurements, but it is, I believe it is industry standard for at least these commercial labs to be testing at 0.1%. So we wanted to do that as well and see how our results lined up. On this plot is showing, in addition to our site, the Sunderland site, and soils from the Sunderland site, it's also showing some data from other silt sites in the Pacific Northwest. And interestingly, at 0.1%, we see that our data is in line with these other sites as well, but not with the Sunderland site. During small strain, is there any fluctuation in normal strain, and is your shear LVDT inside the cell? No, the shear LVDT is not inside the cell. It's I believe that it's outside the shear box, so it's looking at changes in the shear box. And is there any fluctuation in normal strain? I would have to take a look. I believe that there's only kind of the normal fluctuations that you see at the larger strain values. But yeah, I'll have to get back to you on that as we look for, as I go and review the test results.
Hi, I have a quick question. How much of the excess pore water pressure reduction during the T-Rex test is due to the desaturation? And for how much of that reduction the shear strength improvement is responsible for? As you know, we have some interparticle cementation during this process. And this can increase the shear strength of soil and decrease the liquefaction potential.
Yeah, that's a great point as well. So we don't know at this point. So that reduction in saturation that we see from the T-Rex testing, where kind of our knowledge gap is right now and what we plan to work on, it's sort of funny that we're kind of doing this project backwards in a way. We have all these field data and now we need to do lab testing to help us interpret it. So part of that is we plan to do some cyclic testing in the lab at different levels of saturation. So we can understand with these silt soils, just what that change in excess pore water pressure ratio is or in cyclic behavior is as saturation changes. Most of the data that's out there, the published data, are for silica sands. And so it will be interesting to see just how those relationships or how those behaviors change when we start to look at these low plasticity silts. And then, yeah, the second part of your question is if we have a little bit of precipitate between the particles. And again, we don't know. We expect there to be potentially small levels of calcium precipitate from this treatment reaction. The treatment solution was designed, I believe, so that there may have been a little bit of precipitation, but not a lot. And we do plan to do like acid digest tests to see this. Unfortunately, the lab that we need to do those tests is somebody else's lab. And with COVID restrictions, we haven't been able to get into that lab. So it's, yeah, it's something for the future.
Yeah, thank you.
Okay, well, if there aren't any more questions, thank you so much. That was a good Q&A session. I was almost all over my head, but it was good.
Yeah, that was really wonderful. Thank you for all the questions. And thank you everyone for attending tonight.
Okay, and again, we'll be uploading this to our YouTube. All right, thank you. I think that's it. Good night.
Thanks again. Bye-bye.
Bye, y'all.